Hello ladies and gentlemen, welcome to my lecture series Modern Gravitational Theory. This lecture 4, Calculations with Tensors. First, we want to consider some general things about tensors. A scalar is a tensor of zeroth order because there is no set of components. There's no extension of components in any direction. We can compare that with a point in geometry. A point has got the dimension 0, but if we then consider an extension in one direction, a line, a stretch, then this would have the dimension of 1. And so if we consider a vector, co- or contravariant vector, a row or column vector, then we have a tensor of first order because there is an array of components in one direction. Okay. Then if we consider a tensor with two indices, a second rank tensor, like the metric tensor we had introduced in the last lecture, then we have a two-dimensional array of components. Means we have in the four-dimensional space 4 times 4, 16 components. For example, if we have a tensor of fourth order or rank, for example R, the Riemannian curvature tensor. So in the four-dimensional space and 4 indices, that means we have altogether 256 components in this four-dimensional array of components. Then a tensor is symmetric if the value does not change if we exchange two indices. That means here tensor T mu nu is the same like T nu mu. And that's the same for the covariant, contravariant tensor or mixed tensor here in 121. Then a tensor can be symmetric in two indices and not symmetric in other two indices. If we have here a tensor T with 4 indices, four-dimensional space we can say, then here if we exchange nu and mu, then we have a symmetry. But if we exchange alpha and beta, then the values are not the same. So a tensor is antisymmetric if the components change their sign by exchanging two indices. That means here if we have a tensor T mu mu and we exchange the indices, then we would write a minus here. And of course, that's the same again in the contravariant or in the mixed version. Okay. Then a tensor can be antisymmetric in two indices and not antisymmetric in other two indices. Here the same. If we exchange the first two indices and it only changes the minus, the sign plus to minus and vice versa, then we have here antisymmetry in the first two indices, but in the second two indices there is no symmetry. We can obtain the symmetric part of a tensor T by calculating this. If we add the value T mu nu with the value T mu mu, so the antisymmetric values would cancel out, and we have the double value of the symmetric values, and so we must write factor a half here to that expression, and so that gives the symmetric part. And if we want to have the antisymmetric part of a tensor, then we have to write a minus here because this cancels out the symmetric values and the antisymmetric values stay here. And with a factor a half, then, because it's the double value again, then we get the antisymmetric part of the tensor. And of course, if we add those two things again, we get the original tensor. The mu. T mu mu is then the sum of the symmetric and antisymmetric part, or we can write it out here like this in 126. We found sometimes the following notation in the literature. If the symmetric part of a tensor is meant, of a tensor T, mu, mu, then the indices are written in parentheses here. And if the antisymmetric part of a tensor is meant, then the indices are written in brackets. Okay. Then a scalar product of two tensors A and B of second rank here can be written like this. Yeah, we have a tensor A and B, and yeah, a scalar product is a summation over the components, and here alpha is a counting index. Yeah, of course we are using tensors, so we have a covariant index and a contravariant one, and so we can here calculate the scalar product. That means in the four-dimensional space we have got four addends here, 128, and yeah, then two indices, the covariant index of A and the contravariant index of B are vanishing, and so we have a tensor with only two indices again, a contravariant mu and a covariant nu. We were already considering the gradient in a curved space. Now we want to look at the divergence in a curved space. Now we start with Cartesian coordinates in a flat space, three-dimensional space, and we have a vector field V, and so we can write div vector field, or we can write the divergence with a Napler operator. It's a scalar product with the operator and the field, the vector field. And so we would have three components here that should be known from the basic lectures in theoretical physics. Or we can use the expression, the scalar product with the Einsteinian sum convention. We write Vi, E, I, contravariant here. And so we can write instead of three addends only one, where with the automatically summation over I here. Yeah, the vectors, the unit vectors are not dependent on the x coordinates, so we can write the unit vectors outside the differential quotient here. Then we introduce curved coordinates, we call them y again, and we use the chain rule then. That means instead of the differentiation of the v field with respect to the x coordinates, we differentiate with respect to the y coordinates now, but then we have an additional differential quotient dy dx here. And if we use the expression here that the product of the unit vector and the differential quotients of y and x is equal to the g vector, so we can write the divergence of v in this way here, 131. That is g vector, j, contravariant, and v vector differentiated with respect to the y coordinates. With the basis vectors gi, and we can write for v vector in the curved space now, this scalar product. V I contravariant and gi covariant. So we substitute v here in 131, and then we have here this product in the parentheses. So we have two factors here in the parentheses, and so we get, by differentiating that product, two addends. Here in the first part v is differentiated, and so gi is only a factor here. In the second ident, vi is a factor, and g and y is there as the differential quotient. So, yeah, we know the product of j contravariant and gi covariant is the Kronecker delta unit tensor. And we have here scalar product in the index I, and so that means that this I is changing into j because of Kronecker delta. And so we have now this formula in 133. We see the first part that is analogous to 129 here, to this differential quotients in the several coordinates. But here we have in a curved space an additional term. Okay. Here we have used the contravariant components of the vector field V to express the divergence. We now want to use the covariant components also to write the divergence of V. So we use the metric tensor. By using the metric tensor, we can change a covariant vector into a contravariant one, or vice versa. And so now we substitute V contravariant by using the contravariant metric tensor and the covariant components of V. So we have here this differentiation of V with respect to y. Yeah, and an additional metric tensor. And in the second ident, we have, instead of V contravariant, V covariant and the metric tensor. Here we must use a new index, new counting index for this new scalar product, because this scalar product hasn't anything to do with the other scalar products. So a new index must be used here. And then we have here a scalar product in the index I. We have here I contravariant here, and here I covariant. That means this covariant index changes into a contravariant one, and we needn't to write a metric tensor anymore here. So, and here we have got now the expression for the divergence with the covariant components of V in 134. Now we want to consider the rotation or curl. Here we will use the word rotation, and we will write rot in the equations here. Yeah, the divergence, that is the scalar product of the Nabla operator and the vector field. And here the rotation is the vector product of the Nabla operator and the vector field. Okay, that should be known from the basic lectures in theoretical physics. If we want to write the rotation of a vector field, then we have several possibilities. One of them is using a determinant. Though in the first row we have the unit vectors, in the second the differential operators, and in the third row we have the components of the vector field. If we calculate now the determinant here, then we would get this result here, 135. We have 6 idents. Each unit vector has a negative and a positive ident. Now we substitute the coordinates x, y, z by x1, x2, x3, because we want to use a counting index. Yeah, here we start again in Cartesian flat coordinates and in the three-dimensional space. At the moment, here we are not in a curved space. Then, that should also be known, if we have the vector product of two basis vectors, then we get the third basis vector. For example, E1 vector is equal to the vector product of E2 vector and E3 vector. And the indices 1, 2, 3 are cyclical exchangeable. That would make no difference. But if we exchange two vectors, if we write E3 cross E2, then we must write a minus, because then the sign of the result is changing. And so now we substitute each basis vector here. Ex would be E1, and E1 is the scalar the vector product of E2 and E3. And so we do that in all of the 6 terms here. And then we can write, by using counting indices, it's very compact. We can write, rod v vector is equal to the vector product of the two basis vectors, and then the differential quotient of the component of v and x. Okay, the component of v is here projected out by using the scalar product of v vector and another basis vector here, ej. We see, if we look at here in line 136, the second basis vector here and the index of v here are identical, here 3, 3, 2, 2, and so we count here with j over these components. And then here the first basis vector and the index of x here are the same. That's the second counting index here. Okay, we are in a flat space, so co- and contravariant vectors are identical, but we want to use the Einsteinian sum convention, and so we write here contravariant indices in the basis vectors. So we have now only one term, and then the basis vector here, ej, is not dependent on x, so we can write it here out of the differential quotient. But we want to introduce now curved coordinates, and so we use again the coordinates y and the g vectors. And so for v vector we write vk and gk, scalar product here. And then we can write this. We now get for the differential quotients two idents, because here we have a product of two factors. Here in the first, v is differentiated and g is a factor. And here g is differentiated and v is a factor. Now we solve the big parentheses in 137 and get two idents here in 138. Now we apply the chain rule in the first term, then we differentiate v with respect to the y coordinates then. And in the second ident we substitute g vector by e vector and the differential quotient of the coordinates y and x. We have then 139. And we now use again the expression for g vector, e vector, and the differential quotient of the coordinates. That means for this ei here and the differential quotients here of the coordinates, we write g, and though here we have a g then in the vector product. In the second ident we have e vector and e vector, that is a Kronecker delta. Then we continue with the same formula again for the G vector. For gk, we substitute now E vector and new differential quotient of the coordinates here. And in the second ident, okay, we exchange the two basis vectors in the vector product. That means we must write a minus here. And here we have a scalar product in the index m. Here m contravariant and here m covariant. That means the x coordinate here overtakes the j index from the Kronecker delta. Here 141. Now 140, 141 are the same equations. And so the second ident here must be the same in the two equations. So we can write here this with a positive sign must be equal to the expression with a negative sign. The order of differentiation here makes no difference. And so, this is only possible when the term is 0, when it is vanishing. And so we can cancel out here the second ident in the formula. Then we have only for the rotation of V, this expression only one term. Now we have here a Kronecker delta for these two E vectors, Ej, Em here. And then again here, because of the scalar product in the index m, x here overtakes the index j. So we are here in 143. Now again we can write for E vector and the differential quotients of the coordinates y and x g vector. So we write here g vector. And we can say if we have the rotation of a vector field, the result is another vector field. We call it here A vector. Okay, and we can write A vector as a scalar product of the components AI and the basis vectors G, here Gi. So this must be here what we had in 144 for the rotation. Both things must be equal. Then we multiply by another G vector. So we have here a scalar product of two G vectors, Gj and Gi. That is a delta Kronecker here again. And if we multiply here with another G vector, we have here three G vectors. One here is with a vector product and with a scalar product here. And this is a parallelepipedial product. And for this we introduce a new tensor. We call it epsilon. Epsilon, with the indices j, l, k. Here 148. For the j's component of a, aj, we can write now, this. Aj is, the epsilon tensor, and the differentiation of the vector field V with respect to the y coordinates. Or if we write rotation V, so here rotation V is a vector multiplied by a G vector. So here we have a vector, and to get the rotation we must multiply with another G vector here. So we have here another G vector in this expression here, 149. This epsilon tensor is a cyclical one. That means if we rotate the indices j, l, k here in this way, the value remains the same. Epsilon j, l, k is the same like k, j, L or LKJ. But the epsilon tensor is completely antisymmetric in every two indices. So if we exchange in one of these positive expressions two indices, then we must add a minus. So we have here minus epsilon LJK, and so we have here three minus values in 150. If there are two indices with the same value, then the epsilon tensor is vanishing. It's zero then. Now we consider the transformation of vectors. We suppose we have two coordinate systems, one with the coordinates x0, x1, x2, x3, and one with the prime coordinates. Then we have four functions f mu, which yield the prime coordinates. In general, the function f here depends on all coordinates. The functions must be independent and the Jacobi determinant may not vanish. We can write for the Jacobian determinant j the differential quotient with the coordinates, or easily dx primed dx, where the x stands for all coordinates. Or we write out the determinant. Then we have in the first row the functions f differentiated with respect to xo. In the second row with respect to x1, and so on. And there exists an inverse transformation. We call the functions here h. In a former lecture, we had considered the example of a two-dimensional Cartesian coordinate system and polar coordinate system. We suppose we have a curved space. We can consider a vector of the differentials in the coordinates dx mu. This vector has a direction. The same vector can be represented by the primed vector of the other coordinate system, dx mu primed. This other vector must point in the same direction. We use only other coordinates, but the physical things do not change. According to the transformation rules we already had before, we can write here number 155, the most general form. Here we have here dx primed mu equals the differential quotient of the primed coordinates and the unprimed coordinates multiplied by the differential of the unprimed coordinates. Here we have scalar product in the index nu. This is a contravariant index, and here in the denominator this is a covariant index. Or vice versa, if we want to have the unprimed coordinates, dx mu equals then to the differential quotient, where we have now the unprimed x in the numerator and the primed ones in the denominator. And of course we have here the differential with a prime. If we apply a transformation and then the inverse one, then there is no change. That would be a factor of 1. The differentials dx mu are a normal vector, okay, with a differentially small length, but a vector. So we can write an arbitrary vector v instead. So we have the general transformation law for contravariant vector v. Here, 157. Now we want to know the transformation law for covariant vector. We consider the derivative of a scalar function phi, the gradient. We write here in 158 the gradient and apply the chain rule. The derivative of the function phi here is a covariant vector. So we can write 159. And so this is a transformation rule for an arbitrary covariant vector. And now we can transform an arbitrary tensor. Vectors are tensors of first order. Here in 160 we consider a tensor with two covariant and two contravariant indices. We consider the index alpha. Alpha is vanishing because there is a scalar product over this index, and we have to introduce a new index for the transformed tensor, here gamma. And we have here the differential quotient dx alpha dx gamma, like we had derived that before above. And according to that, we have for the beta index here a corresponding differential quotient, and here we have a new index delta. And we have then, according to the transformation rules from above, for the indices mu, contravariant ones, the differential quotients here with the scalar products. Then, for the total differential of a scalar function phi, we have 161. The differential quotient of phi and x is a covariant vector, so we can write v mu covariant. Of course, this scalar product can also be written with a contravariant index for v and a covariant index for dx. Now we finish lecture 4. Next time we will talk about the Euler-Lagrange equations and the geodesic equation. Thank you for watching. See you next time. Goodbye.